Hello, I'm Serene Belhadj, and this is my Lab 5 report on the motion of a slinky. The purpose of this lab is to model the motion of a stretched slinky dropped from static equilibrium as seen in the video, analyze whether the model slinky stays stationary just like the slinky in the video. The preview is that the results depicted the slinky to remain stationary and then have a downward slope. Let's go over the fundamental models that this experiment will touch on. Newton's second law states that the force of an object is equal to its mass times its acceleration. In other words, the force is equal to the rate of change of momentum. The law relates to the total interactions between the system and the surroundings to the changes in the motion of the system. From Newton's second law, we can derive the velocity update formula and position update formula. Newton's law of universal gravitation states that every particle attracts every other particle in the universe with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Drag force is the force that opposes the relative motion of an object. It increases as an object speeds up. Then it becomes equal to the force of gravity and the object falls at terminal velocity. The tension force is transmitted through a rope, string, or wire when pulled by forces acting from opposite sides. The tension force is directed over the length of the wire and pulls energy equally on the bodies at the ends. Here is the tracker video of the slinky. I've aligned the axes to be at the bottom of the slinky. Let's play the video. And here is the position versus time graph, and here are my data values. Here is my code. I've altered the proportionality constant, and I've changed the time to be when the Y position finally changes. And I've applied the momentum principle, velocity and position update formulas, calculating the gravity, the tension force, and the net force. And here in the second while loop, I've adjusted the time and the same calculations for the gravitational force, but then adding the drag force and the net force, and again the velocity and position update formulas. And then running the program, you can see here's a graph remaining stationary and then sloping downwards. Here are the results. We can see that both the computational model and observational model graphs have the same flow where they are stationary for about 6 seconds, almost 6 seconds, and then it starts to slope downwards. However, although when both graphs are stationary, the values align at around 1.76, when the graphs start to slope downwards, the values don't completely align as the computational model slopes downward at a much slower rate than the tracker. When it comes to possible errors, it may be because I have not done the calibration correctly or the center of mass wasn't consistent at each interval. Furthermore, it could be because there were other forces not taken into account, like the tension. So, what does this mean? The tension of the slinky is pulling upwards, and it is balanced with gravity until the whole slinky becomes compressed. After the compression, the slinky finally begins to fall. Therefore, this means that the bottom of the slinky remains motionless until the tension force and gravitational force are the same and cancel each other out.